Welcome to the deep dive. Have you ever really thought about what that word pure means? You see it all the time, right? On milk cartons, spice packets. We usually think, okay, pure just means nothing unwanted has been added. No adulteration. But, from a scientific perspective, pure has a much sharper, much more specific meaning. Today, we're going on a deep dive to sort of scientifically see the world around us. We'll break down things we take for granted, like air or even a glass of water, to understand what they really are chemically. How does a scientist look past that everyday view to find the basic building blocks? We're going to explore the scientific line between pure substances and mixtures, look into their different types, their properties, and, crucially, the difference between physical and chemical changes. Getting this right is absolutely fundamental for your studies and, of course, for competitive exams. And to help us unpack all of this with the right precision, we have an expert with us today.
It's great to be here. Yes, these concepts are, well, they're definitely foundational. Getting them clear really helps build a strong base for chemistry, especially for those exams.
Fantastic. So let's jump right in with that word, pure. How does a scientist define a pure substance, and way does that differ from how we might use the word just, chatting day to day?
That's the perfect place to start, really, because understanding this clears up a lot. Scientifically, a pure substance means something very specific. Every single particle in it, its constituent particles, are chemically identical. It's made of just one type of particle, one single form of matter.
Okay, chemically identical.
Exactly. Now compare that to our everyday use. Think about milk. We often call milk pure, meaning, well, it hasn't been watered down or anything. But scientifically, milk is actually quite a complex mixture. It's got water, fat particles, protein, sugars, all mixed together. They aren't chemically bonded into one single type of particle.
Ah, right. So it's a mix, not a single substance.
Precisely. And that's true for most things around us. Seawater, for example, minerals in the ground, soil. They're almost all mixtures of two or more pure components. So a mixture is just, well, made up of more than one kind of pure substance or pure form of matter. And really key point here, especially for understanding these concepts for exams, is how you separate them. The components in a mixture. You can often separate them using physical methods, like if you have salt water, you can just evaporate the water, right? And you're left with the salt.
Simple evaporation, yeah.
But pure substances themselves, like the salt, sodium chloride, or maybe sugar, you can't break them down into simpler chemical bits using just physical methods like evaporation or filtering.
That makes sense. A fundamental difference in how they can be separated. So if most things are mixtures, how do we start sorting them out? Are they all alike? Or are there different categories?
Good question. No, they're not all the same. We classify mixtures based on how evenly their components are spread out. There are basically two main types you need to know: homogeneous mixtures and heterogeneous mixtures.
Homogeneous and heterogeneous. Okay.
Homogeneous mixtures have a uniform composition all the way through. Everywhere you sample it, it's the same. These are often called solutions. Think about dissolving salt or sugar in water. Once it's dissolved properly, every drop tastes the same. Or remember those copper sulfate experiments? You might make a light blue solution and a dark blue one.
Yes, different concentrations.
Right, different concentrations, so maybe different color intensity. But within each solution, the color is uniform throughout. The particles are mixed at such a fine level you can't distinguish them. That's homogeneity. Heterogeneous mixtures, on the other hand, well, they have a non-uniform composition. You can actually see physically distinct parts or phases.
Like oil and water.
Exactly like oil and water. Perfect example. Or imagine mixing sand and sugar, or, say, iron filings with sulfur powder before you heat them. You can literally see the different bits.
You can pick them out almost.
You can. The components stay separate, and their distribution isn't uniform. That's heterogeneity.
Okay, you mentioned homogeneous mixtures are also called solutions. Could you elaborate a bit more on solutions? What exactly defines them, and what are their key properties?
Absolutely. A solution is, by definition, a homogeneous mixture of two or more substances. We use them all the time without maybe thinking about the term. Lemonade, soda water, these are everyday solutions.
Right.
But it's really important, especially for exams, to remember solutions aren't just liquids. You can have solid solutions too. Alloys are a great example. Think of brass. It's a solid solution, mostly copper, about 70%, and zinc, about 30%. They're mixed so thoroughly at the atomic level, they form a single, uniform, solid phase.
Like they've become one thing.
In a way, yes. And gaseous solutions are common too. Air itself. It's a homogeneous mixture of gases, mainly nitrogen, about 78%, and oxygen, about 21%, plus other gases in smaller amounts. The core idea is homogeneity at the particle level. That's why lemonade tastes the same throughout. The sugar molecules are evenly distributed among the water molecules.
Makes sense. And solutions have components, right?
Yes, typically two main parts. The solvent is the component that does the dissolving, and it's usually present in the larger amount. Water is a very common solvent, like in sugar water. Alcohol is the solvent in tincture of iodine. Nitrogen is the solvent in air.
Okay, the dissolver.
And the other part is the solute. That's the substance that gets dissolved, usually present in the smaller quantity. So sugar is the solute in sugar water, iodine is the solute in that tincture, carbon dioxide is the solute in fizzy drinks, oxygen is a solute in air.
Solute dissolves in the solvent. Got it. What about their properties? You said those are important.
Extremely important. These often come up directly in question. So key properties of a true solution. First, it's homogeneous, as we've established. Second, the particle size is incredibly small, usually less than 1 nanometer. That's 10 to the power of -9 meters. So small you absolutely cannot see them with the naked eye.
Tiny.
Very tiny. Third, because they're so small, these particles do not scatter light. If you shine a beam of light through a true solution, you won't see the path of the beam.
Unlike dust in the air.
Exactly, we'll get to that. Fourth, you cannot separate the solute from the solvent by simple filtration. The solute particles just pass right through the filter paper. And finally, fifth, solutions are stable. The solute particles don't settle down if you leave the solution standing. Your sugary water doesn't suddenly become clear water on top with sugar at the bottom.
Right, it stays mixed. That's a really clear list.
Yeah.
Now, we often talk about solutions being dilute or concentrated. How do we actually measure that concentration? And are there other ways to classify solutions based on how much solute is in there?
Yes, those terms dilute and concentrated are basically comparative. One solution is dilute compared to another, which is more concentrated, meaning it has less solute relative to the solvent. But for a more precise scientific classification, we use terms like saturated and unsaturated. A saturated solution is one that holds the maximum possible amount of solute that can be dissolved in the solvent at a specific temperature. Exactly. It can't dissolve any more solute at that temperature. If you add more, it'll just sink to the bottom. The actual amount of solute present in a saturated solution at a given temperature is called its solubility. And this is important. Different substances have different solubilities. Sugar dissolves much more in water than, say, salt does at the same temperature.
Okay. An unsaturated.
An unsaturated solution just contains less solute than the saturation point. It still has capacity to dissolve more solute if you add it.
So there's still room, so to speak.
Precisely. Now, for quantitative work, especially the calculations you'll face in exams, we need ways to express concentration numerically. There are several common methods, usually involving percentages. One is mass by mass percentage. That's the mass of the solute divided by the total mass of the solution, then multiplied by 100.
Okay, mass over mass.
Then there's mass by volume percentage. Mass of solute divided by the total volume of the solution times 100. And also volume by volume percentage. Volume of solute divided by the total volume of solution times 100. This is often used for liquid solutions, like alcohol and water.
All right, 3 ways to calculate it.
Let's quickly do an example. Say you dissolve 40 grams of common salt in 320 grams of water. What's the mass by mass percentage? First, find the total mass of the solution. That's solute plus solvent. 40 grams plus 320 grams equals 360 grams.
Okay, 360 grams total.
Right. Then the percentage is mass of solute, mass of solution, ec 100. So 40, 360 at 100.
Which is about 11.1%.
Exactly, about 11.1%. Being comfortable with these formulas and calculations is definitely key for problem solving in exams.
Absolutely. So solutions are the homogeneous side. What about the other side, the heterogeneous mixtures where things aren't quite so uniform or maybe look uniform but aren't? Let's talk about suspensions and colloids.
Excellent transition. Yes, moving away from the perfect mixing of solutions, we get into heterogeneous territory. First up is a suspension. This is a heterogeneous mixture where solid particles are dispersed throughout a liquid, but they don't actually dissolve. They just hang there, suspended. Think about mixing chalk powder or maybe wheat flour in water.
You can see the particles floating around.
You absolutely can. And if you let it sit, they'll eventually settle down. That's a key characteristic. So the properties of a suspension are quite different from a solution. 1, it's heterogeneous. 2, the particles are large enough to be visible to the naked eye. 3, because the particles are larger, they scatter light. If you shine a beam through a suspension, you will see the path of light.
Okay, so light scattering happens here.
It does. 4, suspensions are unstable. The particles will settle out over time due to gravity. And 5, you can separate the suspended particles from the liquid using simple filtration. The particles are too big to pass through the filter paper.
Right. Quite different from solutions then. What about colloids? You mentioned they can be tricky.
They can be. Colloidal solutions, or just colloids, are fascinating. They often appear homogeneous to the naked eye, but scientifically, they're classified as heterogeneous. Milk is a classic colloid. Ink is another example. The particles in a colloid are uniformly spread throughout the medium, but their size is intermediate, smaller than suspension particles, but larger than solute particles in a true solution.
So, small enough to look uniform, but big enough to.
Big enough to scatter light. This leads to a very important phenomenon called the Tyndall effect, named after the scientist John Tyndall. The Tyndall effect is simply the scattering of a beam of visible light by colloidal particles. You've definitely seen this.
Like sunlight through a dusty room.
Exactly. The dust particles in the air form a colloid, an aerosol specifically, and they scatter the sunlight, making the beam visible. Or think about sunlight filtering through fog or mist, or through the canopy in a dense forest.
The mist particles are colloids.
Right. Tiny water droplets dispersed in air, they act as colloids and scatter the light. So, key properties of colloids. 1, they are technically heterogeneous, even if they look uniform. 2, the particles are too small to see individually with the naked eye, but large enough to scatter light, Tyndall effect. 3, colloids are generally quite stable. The particles usually don't settle down on their own. Milk doesn't separate easily unless treated.
Okay, more stable than suspensions.
Much more. And 4, you cannot separate colloidal particles by ordinary filtration. They pass through filter paper. You often need a special technique called centrifugation, spinning it really fast to separate them.
Centrifugation, right, like in labs.
Exactly. And just like solutions have solute and solvent, colloids have components too, but we use different terms. The dispersed phase, like the solute, and the dispersion medium, like the solvent. Colloids are classified based on the states of these two phases. You get different types like aerosols, liquid or solid in gas fog, smoke; foams, gas and liquid or solid shaving cream, sponge; emulsions, liquid and liquid milk, face cream; the sols, solid and liquid or solid paint, muddy water, gemstones; and gels, liquid trapped in a solid network, jelly, cheese. Knowing these types and examples is very useful.
That's a great overview of the different mixture types. We've covered a lot about forms of matter. Now let's switch gears slightly and look at how matter changes. What's the core difference between a physical change and a chemical change? This seems fundamental.
It absolutely is fundamental. Correct. Understanding this difference is key to understanding chemical reactions later on. Let's start with physical properties. These are characteristics you can observe or measure without changing the substance's actual chemical identity. Think about things like color, hardness, whether it's a solid or liquid, rigidity, fluidity, density, melting point, boiling point. These are all physical properties.
Things you can see or measure without altering what it is.
Precisely. So a physical change is a transformation that alters these physical properties, but does not change the chemical composition or the basic nature of the substance. No new substance is formed. The best example is water changing state. Ice melting into water, water boiling into steam. It looks different, feels different, behaves differently physically, but chemically. It's always H2O.
Still water molecules.
Exactly. Other examples include cutting wood. It's still wood, just in smaller pieces. Melting butter. It changes state, but it's still butter fat. Dissolving salt in water, you can get the salt back by evaporation. Making a fruit salad, you're just mixing fruits, not changing them chemically.
Okay, clear. So chemical change must be different.
Completely different. A chemical change, which is essentially a chemical reaction, is a process where one substance interacts with another or decomposes, resulting in a change in chemical composition. Crucially, new substances with different chemical properties are formed.
New stuff gets made.
That's the heart of it.
Yeah.
Think about burning something like oil or wood or paper. Burning, or combustion, is a chemical change. The original substance reacts with oxygen, and you get completely new things like carbon dioxide, water vapor, ash.
You can't easily get the original wood back from the ash and smoke.
You can't. The change is irreversible by simple physical means. Rusting is another classic example. Iron reacts with oxygen and water to form iron oxide, or rust, which is a totally different chemical substance with different properties than iron. Passing electricity through water, electrolysis, breaks it down into hydrogen and oxygen gases again, new substances.
Right.
And it's interesting, sometimes both changes happen together. Consider a burning candle, the wax melting near the flame. That's a physical change, solid to liquid. but the wax actually burning in the flame, reacting with oxygen to produce light and heat. That's the chemical change.
That's a good example of both happening. So physical change is about form, chemical change is about substance identity.
That's a great way to put it. Physical change alters form or appearance. Chemical change alters the fundamental substance itself. Grasping this is vital.
Definitely. Okay, having clarified physical versus chemical changes, let's circle back to those pure substances we started with. How do we classify them further? What are the main categories of pure substances?
Right, back to the fundamentals. Pure substances themselves are divided into two main categories, elements and compounds.
Elements and compounds. Okay.
Let's tackle elements first. Historically, Robert Boyle first used the term element back in 1661, but it was Antoine Laurent Lavoisier, a French chemist, who gave it a really useful experimental definition. He defined an element as a basic form of matter that cannot be broken down into simpler substances by chemical reactions. It's the simplest chemical form.
Can't get any simpler chemically.
Exactly. Now, elements themselves are usually grouped based on their properties into three types: metals, nonmetals, and metalloids. Metals you probably have a good feel for. They usually have a luster, a shine. They're often silvery gray or golden yellow. They're good conductors of heat and electricity. They're ductile, meaning you can draw them into wires. And they're malleable. You can hammer them into thin sheets. They also tend to be sonorous. They make a ringing sound when hit.
Like copper wires, gold jewelry.
Perfect examples: gold, silver, copper, iron, sodium, potassium. Lots of familiar ones. There's one key exception to remember for exams: mercury. It's a metal, but it's liquid at room temperature.
Ah, yes, mercury.
Then we have nonmetals. These tend to have a wider variety of appearances, different colors. They're generally poor conductors of heat and electricity. They don't have that metallic luster. They're not typically sonorous or malleable. Examples include gases like hydrogen and oxygen, solids like carbon, and forms like coal or graphite, and sulfur, liquids like bromine. Iodine is a solid nonmetal.
So, kind of the opposite properties to metals, mostly.
Largely, yes. And bridging the gap are the metalloids. These elements have properties that are intermediate between metals and nonmetals. They might conduct electricity somewhat, but not as well as metals. Semiconductors often fall here. Examples include boron, silicon, germanium. Silicon is hugely important in electronics.
Right, silicon chips.
Exactly. Quick facts. There are over 100 known elements. Most are solid at room temperature. Only 11 are gases, and just 2 are liquids: mercury, metal, and bromine, nonmetal. 2 others, gallium and cesium, melt just slightly above room temperature.
Good details to remember. So that's elements. What about the other type of pure substance? Compounds.
All right, compounds. A compound is a pure substance composed of 2 or more elements chemically combined together in a fixed proportion by mass. That fixed proportion is absolutely critical. It's what distinguishes a compound from a mixture.
Chemically combined, fixed ratio.
Precisely. Let's recall that iron and sulfur example we touched on earlier. If you just mix iron filings and sulfur powder, you get a mixture. The ratio can vary. You can still pull the iron out with a magnet, and adding acid reacts with the iron to give hydrogen gas. The original properties are still there.
Okay, that was the mixture.
But if you take that mixture and heat it strongly, a chemical reaction occurs. They combine chemically. You form a new substance, iron sulfide. This iron sulfide is a compound, and its properties are totally different. It's not magnetic anymore. And if you add acid to it, you don't get hydrogen gas, you get hydrogen sulfide gas, which has that distinct rotten egg smell. A completely different chemical behavior because it's a new substance.
Wow. So heating caused a chemical change, forming a compound with totally new properties.
Exactly. That experiment perfectly illustrates the difference. And this leads us to a really important comparison for exams: the key differences between mixtures and compounds. It's often presented in a table format. 1. Formation. Mixtures are formed by just physically mixing elements or compounds. No new substance is created. Compounds are formed when elements react chemically. 2. Composition. Mixtures have a variable composition. You can mix them in different ratios. Compounds always have a fixed composition by mass. The elements are present in definite proportions.
Like H2O is always 2 hydrogens to 1 oxygen by atoms, fixed ratio by mass.
Precisely. 3. Properties. A mixture shows the properties of its constituent substances. A compound has properties that are entirely different from the elements it's made of. 4. Separation. You can usually separate the components of a mixture by physical methods: filtering, evaporation, magnets, etc. You can only separate the elements in a compound by chemical or electrochemical reactions, like electrolysis for water.
That comparison really crystallizes the difference. Physical blend versus chemical bond.
That's a very succinct way to put it. Understanding this table is crucial.
We've covered a tremendous amount of ground today, navigating through what seems simple but is chemically quite complex. This really lays a solid foundation for understanding matter.
Indeed. It's been a thorough deep dive. Hopefully you now have a much clearer scientific understanding of why something like pure milk isn't pure in chemistry terms, but is actually a mixture. You've grasped the difference between homogeneous mixtures like solutions and heterogeneous ones like suspensions and colloids, including that telltale Tyndall effect. We've also carefully distinguished physical changes from chemical reactions, and we've classified pure substances into elements, metals, nonmetals, metalloids, and compounds, highlighting their fixed composition and unique properties.
And knowing these classifications, these definitions, isn't just about passing exams, though it's vital for that. It genuinely helps you understand the world at a deeper level. The food you eat, the air you breathe, the materials you use. It's foundational knowledge.
It truly is. And it leads to an interesting question you can ask yourself now. As you look around, how many everyday things might surprise you if you really think about them scientifically? Are they pure substances or mixtures? Maybe try classifying a few things you see right now based on what we've discussed. It's a great way to reinforce these concepts.
That's a fantastic challenge, a great way to apply this knowledge. We really hope this deep dive has given you clear, precise, and exam-ready insights. For more content like this, more detailed topic breakdowns specifically designed to help you excel in your academic and competitive exams, make sure you subscribe to the deep dive and stay tuned.
In this episode, we covered the following key topics. The scientific versus common definition of pure substances. What are mixtures? Types of mixtures. Homogeneous and heterogeneous. What is a solution? Its components and properties. The concentration of a solution. Saturated, unsaturated, and calculation methods. What is a suspension? Its defining properties. What is a colloidal solution? Its properties, the Tyndall effect, and common examples. The distinction between physical and chemical changes. Types of pure substances. Elements, metals, nonmetals, metalloids, and compounds. A comprehensive comparison of mixtures and compounds.